Welcome back to Algorithms and Uncertainty. Today and also in the following lecture, we will be talking about problems of optimal stopping. This means we are presented a sequence of options and we'll have to stop the sequence at the right point without actually knowing the future options. What could this look like in your real life? Well, there's this nice episode of the Gilmore Girls where in one scene they try to find a future husband. And the way Lorelai and Rory play this game is that Lorelai sees some man, and then for every man she sees, she immediately has to say, does she accept him or does she reject him? Maybe this is something that you also experience in your own dating life, that you go on dates and then you always have to decide, well, is this now the one? Is this the person I want to spend my whole life with? Or do I keep looking? Meaning, of course, I'm rejecting this current person now, in our simplified world now, and this person will not come back to me. Or this is something that you might also experience when you want to buy, for example, a house. When you buy a house, you go see different houses, and then whenever you see a house, let's for simplicity assume now that you immediately know whether this or how much you like this house. And then you can say, okay, do you want to now buy the house or do you reject the house? And the way we are now modeling this is that your decisions are immediate and irrevocable. So you cannot decide to later on change your mind and call a seller of a house that you visited like 2 months ago and ask, well, is this house still available? This won't be possible, so our decisions are immediate and irrevocable. Let's try to model this mathematically. In our setting now, we will be presented n candidates in a sequence. And these candidates have values v1 through vn, which are real numbers, which are non-negative real numbers. And we now see the candidates in some order, say 1 through n. And when observing a candidate, we get to know the respective VI, and we'll have to decide whether to accept or reject the candidate. And of course, the difficulty is that we may accept only a single candidate. And our goal is to maximize the VI of the accepted candidate. So you might now be tempted to approach this by using competitive analysis, which means that we want to be, our solution should be at least an alpha fraction of the best value that we see in our sequence, the highest of the maximum value that we see in our sequence. But unfortunately, comparative analysis is pointless here unless we make further assumptions. And let's see why this is true. We might have the sequence in which the first candidate has a value of 1, the second candidate has a value of 0, or we might have this sequence where the first candidate has a value of 1 and the second candidate has a value of much, much greater than 1. And what will happen here? Well, if you're now running a deterministic algorithm, then it will either accept or reject the first candidate. If it accepts the first candidate, then this will be a bad sequence. If it rejects the first candidate, then it will be really bad on this sequence. And this actually means here that no deterministic algorithm is better than zero competitive. Good. As you will see here, a randomized algorithm would at least be a half competitive, because what could you do? You could just randomly guess whether you stop at the first or at the second position without actually looking at the numbers. But unfortunately, it is an easy exercise to see that generally no algorithm, even no randomized algorithm, is better than 1 over n competitive in this setting, which you can achieve by just random guessing. And this is why we are not doing competitive analysis here, because this is just way too pessimistic. This is just not meaningful what we're getting out of this as bounds, but rather we will introduce some stochastic assumptions. Today we will be asking the question, what happens if these inputs, these values, are drawn from probability distributions and we know these probability distributions beforehand? In the next lecture, we will instead assume that the order in which the candidates are presented is actually random. But today, we assume that actually this order is fixed. So we'll definitely see V1 first, then V2, then V3, and so on. So our assumption for today will be that the VI are drawn from known probability distributions, but the order in which they are presented is just fixed. It is 1 through n, and the distributions may be different. So we assume that VI is drawn from a known probability distribution DI, and the DI are not necessarily identical, meaning that we can actually have a different distribution for the first step than we might have for the second step, and so on. So what could this look like? We might have that V1 is drawn from a uniform distribution on 0, 1, 2, and 10. V2 is drawn from a uniform distribution on 0, 3. V3 is drawn from a uniform distribution on 0, 1, 2, 3. And V4 is being drawn from a uniform distribution on 1 and 2. And the question is now, We know all these distributions in advance, so we'll definitely know what V1, V2, V3, and V4 will be drawn from. We also know that they will appear in exactly this order. So first V1, then V2, then V3, then V4. But what we don't know, of course, is the realization of these random variables. Do we accept them? Do we reject them? This of course depends on the value that we see. Well, what could now happen? This V1, this is the first one that we see. Well, a few decisions are really easy. For example, if we see a 10 here, then we know this is the best that we can ever hope for in this entire game. So yes, we would certainly accept a 10 here. What about a 0? Well, it can't be worse than a 0. So we will definitely reject such a 0. For a 1 and a 2, it's not actually clear whether we would want to accept or reject this, because chances are that there's nothing better, or well, a 1, let's see, why would we reject or accept it here? Well, no, now I'm realizing this is actually becoming easy, because the 1 we will actually be able to also pick in the last round. So 1 we would also reject. But what about a 2? Well, chances are now that here we're seeing a 0, here we're seeing a 0 or a 1, here we're seeing a 1. So a 2 would actually be better than anything that we would see in the future. And I also made this up so that here in all these 3 distributions have an expectation of exactly 3 halves. Which means that in expectation, the values that we here are getting here are actually smaller than 2. But of course, we're drawing from multiple of these distributions. So this is exactly the question that we're facing here. What do we do when we see these numbers, and what is it that we can expect to get in the future? Because those are the things that we will be comparing. To now come to a conclusion, we will first now model this as a Markov decision process, because then all the theory applies that we know regarding Markov decision processes, and we know how to compute an optimal policy. And this is what we will do then afterwards. So how can we capture this as a Markov decision process? Well, what we'll have to define is the state space, the action space, the rewards, and the transition probabilities. And we will do this as follows. So our states will be the form vi, I, vi, where this means now that we are in the ith step. And we've just observed a value of vi. And the actions are, now we can either continue or we can decide to stop the sequence. We have one further state I should mention, namely that we can also have stopped the sequence, which means that as soon as we choose the action stop, We stop the sequence, we move to the stop state, and we get the VI as the reward. So the reward will be that we get VI if we're choosing stop in a state I, VI. And it will be 0 if we're choosing continue. And what will be the transition probabilities? Stop always takes us to the state stopped. And continue in I, VI leads to I plus 1, VI plus 1, where of course this VI plus 1, this will be drawn from the distribution that VI plus 1 is drawn from. One more thing I forgot to mention is that we always have a reward of 0, also not only if we're choosing continue, this also happens if we're choosing stop in the stopped state. Because once we stop the sequence, we once get our reward, we once get the VI, and this is the only reward that we're seeing through the entire game. Then, whenever we're choosing continue, we're not getting any reward. And now by the state space modeled like this, we've captured exactly the knowledge that we have at this point, namely we're in the ith step, we see the VI which was drawn from DI, and interestingly enough, if we choose stop at a certain point, then VI plus 1, VI plus 2, and so on, they aren't even drawn from our probability distribution. Just because we don't really care. So then we just remain in the stopped state. And in the stopped state, we don't actually draw the VI plus 1, VI plus 2, and so on. Now, what is the time horizon and what's the starting state? Well, what should be the starting state? It should be it should be 1, V1. But 1, V1, that doesn't work because V1 is actually a random variable. So what we'll do is we'll introduce an artificial step 0 in which we'll have just a value of 0, which we can in principle stop on, but there's no point in stopping on this 0 value. So we will definitely, our policy will definitely choose to continue there. And this means the first thing that we are doing is the random transition into the state 1, V1, where V1 is drawn from D1. And what's the time horizon? The time horizon will be n plus 1, because we have this first transition out of this starting state, which doesn't give us anything, and then for each of the remaining n steps, we should have the choice between accept or reject, or as I called these actions here, continue or stopped. Now, what do we know about such a Markov decision process? We know that we can actually compute the optimal policy. We can compute the optimal policy by this algorithm which uses dynamic programming. But what we'll do next is actually get a deeper understanding of what the optimal policy looks like, because it is actually much easier to compute than that you have to go through this entire table. By the way, how big is this table? How many states do we have? Well, this now depends on how many different values of vi we can have. This might be actually pretty many. Maybe vi doesn't even have finite support, so we might have infinitely many states. For today's lecture, I'm actually assuming that vi only has finite support, so that we have finitely many states. But as a matter of fact, everything that we're doing with a little more careful work, being a little more careful about the infinite sets, this would also work in infinite, in the case that vi has an infinite support. But what I want to do next is understanding the optimal policy for this setting. Let's now try to better understand the optimal policy for this Markov decision process that we've just defined. What do we know? We know that this optimal policy will, its reward will be expressed in terms of the recursive inequality that we derived. Namely, what do we know? We know that in any Markov decision process, we have that the value or the expected reward of an optimal policy starting in state S, or the time horizon of t, is given by take the max over all actions, and now see the immediate reward that you're getting, and take the sum over all states. What's the probability that you're getting into state S prime? And what is the expected reward that you're getting from the state S prime if you have only t minus 1 steps? So what will this look like here? Recall this, that these states S are these pairs I, vi, which means that we are in the ith step and that we've just seen a value of vi. And the t is exactly n minus I plus 1. So what's the expected reward that we're getting? Or more, this is the one question. And the other question is, what should we choose? Which action should we choose? So our actions will be stop or continue. And if the optimal policy chooses stop, then what do we have? Then the immediate reward that we're getting is VI, and we're getting nothing afterwards because this part here will be 0 because we are transitioning to this stop state. And this will then have to be at least what we could get if we were to choose continue. Then we would not get any immediate reward, and we would now move to a random follow-up state, which we can now say, okay, we now draw VI plus 1 from our distribution, and we now ask, what is the expected reward that we're getting from this point onward? And if it chooses continue, then we'll have the exact same inequality but the other way around, namely that now the right hand side will have to be bigger, or at least as big as the left hand side. So what does this mean for us when we are trying to find the optimal policy? Apparently what matters is how does VI compare to this term here. If VI is at least this much, then we should stop. If VI is at most this much, then we should continue. Okay, there is now the thing that if we have equality, then both sides are equally good. Then, well, either choice is equally good. Then, well, there is an optimal policy which stops, as well as there is an optimal policy which continues, because the optimal policy is not necessarily unique. But what we are seeing here is that apparently VI has to be at least something. What we'll still have to understand is what is this something that we have here, and how do we compute this? Because does this look any meaningful? Yes, fortunately it does. What does this term here mean, this something? This something means we are now drawing VI plus 1, and then we are asking what is the expected reward from n minus I steps starting with VI plus 1. But this here is actually nothing but the expected reward of an optimal policy which only starts with being presented VI plus 1. So our original problem was what is the optimal policy for the problem where I presented V1, V2, V3 and so on. But now of course also for the subproblem where we are only presented VI plus 1, VI plus 2, VI plus 3 and so on, there is an optimal policy which has an expected reward. And the thing that we're now asking is what gives us a higher reward? Stopping, meaning that we get the VI immediately, or taking the chance and seeing what is the expected reward of an optimal policy if we are just starting, if we were only starting with VI plus 1. And this leads us to the point that the optimal policy will be a policy which accepts VI if it is above some certain threshold, and this certain threshold is exactly the expected future rewards that we would get if we were only starting now. And more formally, this looks as follows. We say that it is an optimal policy to use thresholds tau 1 up to tau n, such that in the ith step we accept if Vi is bigger than tau I, and reject if Vi is smaller than tau I. And we now also get a very simple formula. The thresholds are defined recursively by tau n being 0 and tau I being the expectation of the maximum of Vi plus 1 and tau I plus 1. And the optimal policy is unique up to tie-breaking at Vi being equal to tau I, which is irrelevant. Okay, so this statement isn't actually super surprising given that we've already seen this formula, except for one thing, namely that this formula for these tau i's is so simple. And maybe let's first see what an optimal policy for our earlier example looks like. So what was this example? In this example, we had V1 being drawn from a uniform distribution on 0, 1, 2, 10. V2 being drawn from a uniform distribution on 0, 3. V3 being drawn from a uniform distribution on 0, 1, 2, 3, and V4 being drawn from a uniform distribution on 1 and 2. And now we are interested in these thresholds. And the question is, how big will these thresholds be? How big is tau 4? Tau 4 will be 0. This is just what we wrote here. Now, how big is tau 3? Tau 3 is the expectation of the maximum of V4 and tau 4. Tau 4 is 0. So this is nothing but the expectation of V4, and this will be 3/2. Now, how big is tau 2? Tau 2 will be the expectation of the maximum of V4 or V3 and tau 3. So this is the expectation of the maximum of V3 and 3/2. we'll have here, this is what V3 is drawn from. And now we see, okay, with probability 1/4, we'll see 0 here, so the maximum of the two will be 3/2. With probability 1/4, we'll see here a 1, which means the maximum will also be 3/2. And then with a 1/4 we see 2, and with probability 1/4 we see a 3, in which case the maximum will be 2 and 3 respectively. So what we're getting here, let me try to squeeze this in, is that we're getting a 1/4 times 3/2 plus a 1/4 times 3/2 plus a 1/4 times 2 plus a 1/4 times 3. And if you now do the math, then what you'll see is that we're getting 2 here. And now we can also figure out what T1 will be. It's the expectation of the maximum of V2 and tau2. So it's the expectation of the maximum of V2 and 2. And this is equal to 1/2 times 2 plus 1/2 times 3. So it will be equal to 5/2 or 2.5. Okay, so this is what comes out of this formula, these taus is it that we're getting. And what does this now mean? What was our initial question? Would we stop at a 2 here? This was one of our questions. And the answer is no, we would not stop at a 2 here, because the threshold that we have here is 5/2, which is bigger than 2. So here we would only stop at a 10. For the second V2, would we stop there for a 3? What's tau2? Tau2 is 2. Which means, yes, we would stop with a 3, we would not stop with a 0. And what is tau3? It is 3/2. So, which we will stop with a 2 or a 3, we wouldn't stop with a 0 or a 1. And here we would always stop, because tau4 is 0, and also because this is reasonable. In this last step, we should of course always stop. Good, so this is something that you can actually easily compute, this optimal policy. And what we still have to do is, of course, prove this theorem, although we are actually pretty far with this, because we've already seen that this is what the optimal policy will do. So the only thing that we actually have to do is we'll have to see that this here corresponds actually to our tau I. So for our proof, we will show that tau I is exactly equal to the expectation of V star of I plus 1, Vi plus 1, n minus I, which means that we are starting the entire game only in step I plus 1, and we ask what is the expected value that we're getting from only this subgame where we're starting with step I plus 1. And we will prove this by downward induction, meaning that we start with I being n, and then we'll show this down to 1. And so the induction base was what? We'll have here tau n, which we say is 0, and here we have n plus 1 and vn plus 1 with a time horizon of 0. So maybe technically we didn't even define this state, but it doesn't matter because there's no more time left. So we'll have that both these sides will be equal to 0. Which means after the last step, you are not getting anything, of course. This is the induction base. Now the interesting thing is the induction step. What is this thing that we have here on the right hand side? And by that I mean if we are now considering here an I rather than an I plus 1, then we would have that V star of I comma Vi comma n minus I plus 1. How big is this? What's the expected reward when you are starting from a state I comma Vi and you have this many steps left? Well, we know that this is of course given by this recursive formula. And now we can also see what these terms are like. This is something that we have already done. Namely, this part here, this is exactly how much? This is exactly Vi if A is equal to continue, is equal to stop, because then we are collecting a reward of Vi, and otherwise it is the expectation of V star of I plus 1 comma Vi plus 1 comma n minus I. And what do we get for this part here? We get that this is exactly equal to tau I by the induction hypothesis. So this means that for the black part is exactly the maximum of Vi and tau I, and so this implies that the expectation of V star of I comma Vi comma Ni plus 1 is exactly the expectation of the maximum of Vi and tau I. And this completes our induction proof. What did we prove? we proved that the expected reward that an optimal policy gets if it is starting from step I plus 1 is exactly what we defined by our recursion as tau I. And moreover, it also tells us, this Brown result also tells us what an optimal policy is like. Namely, what would be an optimal policy? You always take, in every state, you always take the action which gives you the maximum in this part here. And now, of course, you take stop if Vi is at least tau I, and you choose continue if tau I is at least Vi. And if Vi is equal to tau I, then we don't care. Because both of these values are actually equally good. So we have an optimal policy in both cases. And this proves our theorem. By the way, one more thing that we did not explicitly show that we claimed in our theorem was that these thresholds are non-decreasing. Why is this? Because here, by this formula, they are immediately non-decreasing if tau I, let me maybe show it here, tau I will of course always be pointwise at least tau I plus 1 regardless of Vi plus 1. Regardless of what you're seeing here for Vi plus 1, this maximum will never be smaller than tau I plus 1, so also the expectation will be at least tau I plus 1. Good. So, as you see, finding the optimal policy isn't actually super difficult here. The only thing is you have to solve this recursion. And you can even understand the expected value of an optimal policy, namely by also going through this proof and seeing what would be the respective tau 0 that you would be computing this way. Because this would be nothing but the expected value of your, or the expected reward of your optimal policy. And also in our example, we could do this. So we would now take the expectation of the maximum V1 and tau 1, and this gives us exactly the expected reward of our optimal policy. But what this does not give us is a comparison to the offline optimum. Because this is still something that we want to understand. How much are we losing due to the fact that we don't know beforehand what the numbers in the sequence will be? And this is exactly the question that we will be trying to answer now. We don't know what an optimal policy looks like for our case here. Namely, we just computed these thresholds and we accept a number if it exceeds its current threshold, and we reject it if it is below the threshold. If it is equal to the threshold, we don't care. So among all policies, this gives us the highest possible reward, the highest expected possible reward. But what we'd like to do now is we would like to understand how does this actually compare to an offline optimum. So suppose you were actually seeing the entire sequence in advance, where would you stop? Well, certainly at the highest value. How good is this optimal policy compared to this offline optimum, which just stops at the highest value? And interestingly enough, we are able to bound this here. Namely, we can bound this as follows. The optimal policy's expected reward is at least a half times the expectation of the maximum of all Vi. So what's the statement here? We take the optimal policy and we ask what's its expected reward, and we compare it to the maximum number that we see in the sequence. And what we show, or what we will be able to show, is that the ratio is at least a half, so we're getting at least half the value that the optimal policy is getting in expectation. This kind of a theorem is also called a profit inequality. Why that? Because what this is now doing is it is comparing our policy, which is kind of like a gambler, not knowing the future, just, well, betting on what we will be seeing in the future. And this is what we're comparing to a prophet who actually knows the future, who knows everything, who knows what's going to happen. And also our gambler gets at least half the value of the prophet. Good, so how do we show such a statement? Well, we actually would have to only compare the expected reward of our policy with the expected maximum that we see in the sequence. Unfortunately, this comparison is pretty difficult because we were not making any statements whatsoever about this thing here, the expected max. And also understanding what this policy does, even for very simple cases, is somewhat complicated, and therefore we will approach this proof in a little differently. Namely, what we'll do is we will devise some other policy. For this other policy, we will prove that this expected reward is at least a half times the expected maximum value. And this, of course, means that the optimal policy will certainly be this good. Namely, what we'll do is we'll consider the following single threshold policy. We will set just one threshold of tau being equal to half the expected maximum, and we stop the sequence at the first I for which Vi is at least tau. This is certainly a policy, also in our sense, but it is clearly a suboptimal policy. The optimal policy will always be smarter. For example, now in the last step, we even have our threshold, which is not zero. Even in the last step, we might not be rejecting, but this policy is much easier to analyze. And because the optimal policy's expected reward can only be better, bounding the expected reward of this policy is just enough. By the way, This policy is also interesting for some other reasons, namely that we now have just one fixed threshold, which makes this policy even easier for certain applications. But for now, let's just only use this as a comparison, as the point of comparison in between the optimal policy and the profit, which knows the sequence in advance. And our proposition is now the single thresholds policy has an expected reward let's call this V of pi, and we want to show that this is at least a half times the expected maximum value in our sequence. Let's prove this. We set Q to be the probability that all of these V's are smaller than tau, which means that Q is the probability that the sequence is not stopped at all, because we would stop the sequence at the first I for which Vi is at least tau I, but if all of the V's are smaller than tau, then we wouldn't stop the sequence at all. And furthermore, we set Ui equal to Vi minus tau if the sequence is stopped at I and 0 otherwise. Now, what's the expected reward of our optimal policy? The expected reward of our optimal policy is exactly the expectation of the sum of these Ui plus 1 minus Q times tau. Why is this? Because it may happen that our policy does not stop at all, in which V of p is 0. V of pi is 0. Otherwise, it does stop somewhere. And then what we'll have is that the respective Ui will be Vi minus tau I, and then we can also add one further tau. So it will be Vi minus tau, and we can add one further tau so that we are getting exactly the Vi at the point where the sequence is being stopped. One way to also think about this is to say we are selling an item at a price of tau, and we're now asking, well, if the buyers have values Vi and they approach now the market one after the other, what would their utilities be? And the first one who buys the item, the first one who has a value of at least tau, will have a utility of Vi minus tau. And then, if there is any, then we are also getting a revenue of tau. So the expected revenue is 1 minus Q times tau. And this here, this is the expected revenue that we're getting from the buyers. And overall, this is what would then, in algorithmic mechanism design, be called the social welfare. Good, but now what we want to do is we want to bound this term here, and to this end we will now say that what is Ui? Ui is the maximum of Vi minus tau, 0 times the indicator that v1 was less than tau, v2 was less than tau, and so on up to vi minus 1. They were all less than tau. So by this here, I mean this should be 1 if all of these are fulfilled and otherwise 0. So this lets me now write the expectation of ui as the expectation of this thing. And now we are using that these are actually independent random variables. So we get the expectation of vi minus tau, 0, times the probability that vi was less than tau, and so on up to vi minus 1. They were all less than tau. And what do we know about this probability here? This probability will be at least q, because q was the probability that the sequence is not stopped at all. This is the probability that the sequence is not stopped within the first I minus 1 steps. So what this gives us overall is that this is in combination at least the expectation of the maximum of vi minus tau and 0 times q. And this lets us now write the expectation of the sum of these ui. This will be at least the expectation, already using linearity of expectation here, of the sum of the maximum of vi minus tau and 0, and this times qi. And how big is this here? This is a sum of non-negative random variables, so this is at least the maximum of these non-negative random variables. And this is at least the maximum of vi minus tau. So this here is at least the maximum of vi minus tau times q. Good. So now we've bounded this part. And we can now add this part to get v of pi. So this lets us now write v of pi as, recall that this is the expectation of the sum of the ui plus tau times 1 minus q. And now I'm realizing that I forgot to write the expectation up here. This will be important in a second, because now we can plug in this bound here. So this will be at least the expectation of the maximum of the vi minus tau times q plus tau times 1 minus q. And we can also move the tau here outside of the expectation, so we'll get the expectation of the maximum minus tau times q plus tau times 1 minus q. And now the interesting thing is, so far we did not use the definition of tau at all, and we didn't use what Q is either. But now by our definition of tau, this will be exactly a half times the expected maximum of the VI. And also this here, this will also be nothing but a half times the expectation of the maximum of the VI. So this will be a half times the expected maximum of the VI times Q plus 1 minus Q. And this thing here, this is simply 1. So we're getting our desired bound. Good. So this completes our proof, and I hope that you realize that none of these calculations are actually super difficult. Nonetheless, you might realize, okay, they are maybe not super intuitive. What is it that we're actually doing here? And the point is, we are choosing this tau so that we actually don't care what the Q will be. Because it is difficult to understand for arbitrary probability distributions if we set a tau, what will the respective Q be, because they are also arriving in just some order which we have no real influence on. These are different distributions. This makes everything very complicated. But what do we do instead? Well, you can think of this maybe in terms of a case distinction, although we are not doing explicitly a case distinction here. But what you see is that if it is very unlikely for the sequence to be stopped, then this Q would be big, meaning that this first part will be big. If the Q is small, which means that the sequence is very likely to be stopped, then the second part is big. And so what you could maybe as a first approach do is you could distinguish between what if the probability is at least a half or at most a half, and then you would see, okay, in either case I'm covered. This would give you only a factor of a quarter. Here we are now a little smarter and taking into consideration both parts, regardless of what this actual probability is. Good. So once again, the idea here was to consider a simpler policy, because this simple policy we could analyze much better than if you were trying to do this with the optimal policy, for which all these thresholds would be different and we couldn't just do all these all the simple steps that we did actually in these calculations. As a matter of fact, this factor of a half cannot be improved. You'll find the respective example in the lecture notes. But what you can actually do is you can extend this to other settings, like to matching settings or also to matroid settings, if you've heard of this. There is a real industry of profit inequalities that has arisen over the last 10 to 15 years. Good. So this concludes our lecture for today. We've got to know one example of how to model this optimal stopping problem. This was using known probability distributions, but just the numbers arrive in some arbitrary order, which is just fixed beforehand. So we get to see the first in the first step, the second in the second step, and so on. In the next lecture, we will again consider this problem, but in a slightly different way. Namely, then we assume to not know any probability distributions, but instead the numbers arrive in random order. Then this problem is known as the secretary problem. Maybe you've even heard of this before. And this we can also model as a Markov decision process, although the modeling will be a little more surprising, a little more difficult. This is what's happening next time. Until then, I hope you'll let me know if you have any questions. Stay safe. Have a good time. Bye.